obviously is different. So today we are in fact not in Berlin. As you can see, I'm giving this talk from home. I'm in London because of everything that's going on in the world right now. But I think considering that with C++20, we actually got really lucky because we actually did have a C++ committee meeting in Prague in February this year. And that's a picture of everyone who was there. I'm somewhere in that picture, so if you want to play Where's Wally, then you can try to find me. And actually, at that meeting, we finished the technical work on C++20. And that was just a few weeks before the WHO declared a worldwide pandemic and everything started to shut down. And I say this was pretty good timing, right? Because we just finished the technical work on C++20 before this whole thing started. And since then, C++20 has taken all the bureaucratic hurdles to be approved. And so now we're basically just waiting for it to be formally published on the ISO website, which hopefully should happen in a few weeks. And yeah, so basically C++20 is done, which is great. You saw in the previous picture that the C++ committee has actually grown in size quite significantly since the 90s. And so has the C++ standard document. So here's a graph showing how many pages there are in the different versions of the C++ standard document. And you can see C++98 had 700-something pages, and C++20 now has about 1,800. And from the number of pages, it's not immediately obvious which of the C++ standard version were the most significant in terms of impact on the C++ system. And what I mean by significant is not just adding cool new features that you might choose to use, but actually fundamentally changing the way you write C++ code, changing the way we think about C++ code. And I think the last such release that accomplished that before C++20 was C++11. And let's remember why. Let's remember how we had to write code before C++11. So let's say we have a two-dimensional, like a vector of vectors, because we still don't have a good two-dimensional array type in the standard library. So let's say we have a vector of vectors. And before C++11, if you wanted to iterate over this thing, you have to spell out the iterator type, right? Because we didn't have auto. So, and they could be like arbitrarily long, really, and arbitrarily ugly to spell. And then if you wanted to sort this this vector, we had still sort and all the other STL algorithms, but we didn't have Lambdas. So we would, in order to create a custom sorter, custom comparator, you would have to actually write out like a new class, right, and pass that in. And then finally, whenever we had nested templates like that, we actually had to put in an extra white space in between the pairs of closing angle brackets, because the lexer would always treat two angle brackets as a right shift operator, right? And finally, we couldn't even initialize a vector like that because we didn't have list initialization. So in order to initialize a vector, we had to either write a bunch of pushbacks, so we had some horrible boost macros to accomplish that, and some of you might remember that. And it was all really quite painful. And since C++11, we do have auto, we do have range-based for, we do have lambdas, and we do have all these things. So we can write the code like that, right? Which looks a lot more familiar to us and a lot more clean and a lot more readable. And so the addition of all these features has very significantly changed the way everyone writes C++ code today. If you look again at this graph, it looks like C++20 didn't actually add as many pages as C++11 did, right? In fact, actually C++17 added a few more pages to the standard than C++20 did. So it seems that C++20 isn't more significant than C++17 was, but it turns out that counting pages is actually very deceptive. C++20 actually added a lot more material than it seems, because, well, first of all, for C++20, we had to change the paper size of the actual standard document from US letter to A4 because of new ISO requirements. And that made C++20 shorter by several hundred pages, right? So actually the increase is a lot bigger than what it seems in terms of content. And also most of the new pages in C++17, actually, they are kind of due to new library features that came from Boost, things like file system, any, variant, optional, which take up a lot of pages, but don't really give us anything new that really wasn't there before at all. We did add a few language features, things like structured bindings, things like class template argument deduction, which I've done a few talks about in the past. But I would argue that those things are kind of mostly syntactic sugar. They let you write things a bit differently, a bit more conveniently that you already could do. But C++20 really changes the language much more fundamentally. It changes the way we think about code. It changes our mental model of what a function is, what a template is. How do we design a library? How do we organize, package, and compile a C++ program, right? And it kind of touches all of these areas. And that's why I think C++20 is actually the most significant update of C++ in all its history. And in this talk, I want to explain why I think that is. So last year at this conference in Berlin, I actually gave a talk about C++20. I gave a talk about a lot of the small features that are in C++20. But the reason C++20 is so significant is not because of any of these features that I was talking about last year. It is because of the big features. And those specifically, some of you call them the big four, are coroutines, concepts, ranges, and modules. And in this talk, I really want to drill down and talk about those. And let's start with coroutines, because coroutines are really, really cool. But before we can talk about coroutines, we have to talk about functions. What is a function? What is our mental model of a function? Essentially, a function, the way to think about this is it's a chunk of code which has a name. You can call it. You can pass it maybe some parameters, which now isn't really important. It has some local variables, right? And then it executes some code, and then it can return a value. So that's basically our mental model of a function. Turns out that idea of a function, or a subroutine as it used to be called, has been around since the 50s. So that's really nothing new. So let's look at what we can do with those functions. Let's say we have a function f, and then what we do is we want to call it, and then it's going to return a value, and then we're going to print that value, right? So let's say the function returns 0, and then obviously it's going to return 0, then we're going to print 0, right? So this is kind of, pretty much, not very surprising. There is this concept of a pure function, which basically gives you the same output every time, so that if you call f 3 times, you're going to print 0 3 times. And this is probably not really interesting. But what if you want this function to return different values every time? And that makes it a bit more interesting. So let's say you want to generate a sequence. So instead of printing 0, 0, 0, you want to print 0, 1, 2, 3, let's say. How can we achieve that? So obviously, the simplest thing that we can do is we can just write a loop, right? Just in the main function, just write a loop that just prints those values. But that's kind of not how you design code, right? Because you want to separate generating the sequence from printing it, right? Those are two different things. You want to separate them. And how can we achieve that? Well, we can create a container that's holding the sequence, right? So then we generated the sequence, and then we can print the contents of that container in a separate step. So we have separated generation from printing, but now we have this container, and that's holding the whole sequence, right? So we have to initialize it, maybe like this, using list initialization, or maybe we can fill the vector using a loop, or since we don't like row loops, you can fill the vector using an algorithm. There is actually an algorithm in the STL that generates the sequence, and we'll talk about algorithms later. But the downside of this kind of procedural approach is that now you need to store the whole sequence in memory, right? So, and if you want to print all numbers from 0 to 1 billion, then that is probably not a great approach, because maybe you can't create and hold in memory a vector that's that big. So what we want to do instead is we want to generate the sequence lazily, right? We want to generate a new number on demand as we print it, because that's a much more efficient way of doing this. But we still want to separate generation of the sequence from printing. How can we do that? Like, think about that for a second. And maybe what we need to go back to the idea of using a function. But how do we now implement f? Like, how do we implement f such a way that the first time around it prints 0, the second time we call it prints 1, etc., etc.? Okay, so if you think about this, there is one simple way you could do this, which is you could make the counter a static variable, which will then kind of persist. But that will work. That will print the sequence. But now you just introduced global state, right? And that is not a great thing to do. So how do we solve this without introducing global state? And now, well, the most straightforward way, it seems, is to create a class, right? So now we have this myGenerator class that you wrote, which is going to be generating the sequence. And now we keep this counter as a member variable. And now we have this call operator, which returns the current value and then increments the counter, right? And inside main, we now create an object of this type. So we create an instance, so it's not global state anymore. So it solves that problem. And now we call that object to generate more numbers. And that's basically object-oriented programming, right? But so we all know this. We've all been doing this, probably for decades. But I would argue that for a task like generating a sequence, this is kind of the wrong approach, right? Because think about what we have to do here. We need to create a type. We need to decide what member variables that type should have. We need to decide whether it should be private or public. What API does this class have? What public member functions are we going to introduce? What class invariants does this class have? We think in objects, right? And for a task like generating a sequence of numbers, that's way too complicated. That's the wrong way to think about this code. So okay, there's one way we can make this a little bit simpler. Since C++11 we have lambdas. So we could write this as a lambda, so it would look like this. It's shorter, but it is still exactly the same object as before, right? This is just the same as on the last slide, except with a bit of syntactic sugar on top, right? So we still have to explicitly create this object, and we have to explicitly create the state in form of this member variable, which now goes into this init capture, the I equals 0. But it turns out, actually, we don't need to do this. We don't need to think in objects at all. Let's go back to functions. A function like this already has state. It's just the local stack variables, right? This is state. So we can use this. We just need to expand our mental model a little bit of what a function is. So let's imagine a function that has some local variables, like every other function, like this x here. And then it's executing some code. But now it can yield an intermediate value. So it can yield a value like the x, for example, and that will return control to the call side. But now the next time you call f, it's not going to start from the top, but instead it's going to be still where it was after the yield. So it's just going to jump back to where it was, and it still remembers all its local variables. And now it just keeps going until the next yield. And then it keeps going until the next yield, and the third time you call it, and the story repeats. Or until it reaches a return statement at the end, and then it's finished. And that is basically what a coroutine is. So coroutine have been around for almost as long as functions. And as Walter Brown actually pointed out to me just a few days ago, Melvin Conway actually coined the term coroutine in 1958. And there were things in the 50s which arguably you could say are coroutines, like, for example, interestingly, Fortran's print statement with the formatting that it has is arguably like a coroutine. Anyway, Conway then published his explanation of what a coroutine is in 1963, which is this paper here. And by the way, that's the same Conway that coined Conway's law, but it's not the same Conway who invented Conway's game of life. But anyway, so coroutines have been around since forever. And so after 6 decades, essentially, we C++ people finally caught up with everyone else. So I think that's great. So we have coroutines now in the language. And if you think about the previous slide and now how to apply it in this code to generate this sequence, once kind of you understand this idea of a coroutine, it seems intuitive that this code should look something like this, right? So we have this coroutine at the top now, f, which now the counter is just a local variable. And now we have a loop which increments the counter and yields the current value, right? So it yields 0. And then next time you call it, it's just going to jump back into the body of that loop and yield 1. And then it will yield 2, and so on and so forth. So if you call f multiple times, you kind of just keep incrementing the counter and yielding the new value. And that's super simple. So it can just go on like this indefinitely. And you don't have to store the whole sequence. You just create the numbers on demand. Unfortunately, this is C++, so things are not quite as simple. Actually, this code will not compile because of 2 reasons. So the first reason is that actually, instead of the keyword yield, like in most other programming languages, we have a keyword called co-yield because of reasons. So I'm not going to talk about that now. Feel free to ask me about that later. But yeah, so that those keywords have this co_ prefix. And now, the more interesting thing is that in C++, you don't actually directly return this int. You have to return a generator from this coroutine. And then you have to call the generator in main to get the new values, right? So you have this extra step. And that's because C++ is not lying to you. It's telling you what actually happens. And what actually happens is that a coroutine doesn't actually return an int. It returns an object which, through the coroutine API, will eventually give you an int. And the way to think about this is that a coroutine is essentially a generator factory. So you call it to get a generator, and then the generator will give you the values, 0, 1, 2, 3, the stuff that you want. And this extra step is there because there are a bunch of choices how exactly this generator object should work. And C++ lets you make those choices, right? So that's why C++ makes this generator object explicit and gives you the option to implement it yourself and exposes the whole underlying machinery, which is the coroutine API. And that's what you need to use in order to implement that generator. So you can implement it in the way you want, so it will have the behavior you want. And this might be quite confusing. So I know it was very confusing for me. First time I had to wrap my head around this. So let's take this apart. We have your user code, right? That's the code that's calling the coroutine, getting a generator G from the coroutine F, and then using G to get our numbers and print them. So G here is a local variable, right? So it's allocated on the stack. And G contains a bunch of stuff. So first of all, we somehow need to get our int from somewhere, right? So that we can print it. So G, the generator has this thing called the promise type. And that's the first thing that will be instantiated if you create this G. And that's essentially the box where the coroutine puts the int into and the user type gets it from. Think of it a little bit like a std optional of int, right? It's a reusable box that can hold a single int value. And that's essentially the communication channel, right? So everyone needs a reference to that. The coroutine will generate the int and put it into the box. The generator would take it out of the box and return it to a user code. The other thing that's part of the generator is this thing called std coroutine handle. That's an object. And that's kind of a magic standard library type. And what it really is it's a pointer to a coroutine frame. Now, what's a coroutine frame? Think about a normal function. That has a thing called a stack frame, right? So that is basically an internal data structure so that your machine needs to know, so it knows how to call a function, right? And that's how every function works under the hood. And for a normal function, the stack frame contains basically the local variables, the parameters, and an address where to return to. Basically like an address, so that's where it's going to put the return value into. And for a function, the lifetime of the stack frame, as the name says, is tied to the stack, right? So when a function returns, then all the local variables get destroyed. Now for a coroutine, it's pretty much the same thing, except the coroutine frame contains, it also contains all the local variables and how to call it, but the difference now is that this state can persist, right? So when a coroutine yields, that state is still there and the local variables are still there. So that means that the difference is that the coroutine now has a lifetime which is independent from the stack. So that's why you need this pointer to it. So you can manage the lifetime of that coroutine frame, which now will be on the heap. Another way to think about this is think again about this lambda. So this init capture here is a little bit like the coroutine frame, quote unquote, for this lambda, because it has all of its local variables and basically later, so it creates this like state, right? It creates the local variable, which in this case is just the integer. And later you can enter that state again whenever you want because it's stored as a member variable just by calling the lambda. So the coroutine, and that kind of happens implicitly, right? So you don't write out like a member function. It's just the compiler does that for you under the hood. And the coroutine really is just an extension of that. The extension actually is that it does that, but it also has multiple entry points and multiple suspension points, right? But it still has only one coroutine frame that persists, and it persists all the time, just like it does with this lambda. So you can think of this lambda really as a very simple coroutine, except that the lambda has to be entered from the top, and it will run, and then it cannot be resumed. It will like enter from the top again next time. And the coroutine in that sense is more powerful because you can enter it from the middle and you can leave it in the middle. And the other difference is that this coroutine frame for the lambda, which is just this integer there, we know how big it is, right? Because you wrote it. It contains just one integer, which is like 4 bytes or something. So the compiler knows that, so it can put that onto the stack. With the coroutine frame, in general, the compiler doesn't know at compile time how big the coroutine frame has to be. So it has to dynamically allocate it on the heap. And now we understand what the coroutine handle is. It's basically a type erased pointer to that dynamic object, right? So it's like, in a way, it's a little bit like other type erased objects like stud function, which is also kind of like a handle to a type erased object. So that's the coroutine. That's a coroutine frame. And then the generator really is just this user-facing object that groups these two parts of the state together and then forwards the coroutine API to the user code. And again, important, the coroutine frame is on the heap, but the generator is on the stack. So when G goes out of scope at the end of your user code function, then the coroutine frame should be destroyed, and that heap memory will be deallocated. So again, it's a little bit like stud function in that sense. Now, really, the last piece of the puzzle is the actual coroutine, which is this red thing on the right. And that basically constructs the coroutine frame and then runs the code inside the coroutine body, which is the code that you wrote. And the important thing about that is that this coroutine object itself, that's generated by the compiler. So the compiler has to do that, because then the compiler can optimize it. And that is subject to optimizations, which are very interesting. There are actually two important optimizations here. The first one is that actually the compiler will go ahead and turn this code into the right on the right that you wrote, and it will turn it into some complicated state machine to make this whole reentrance behavior kind of more efficient. But you don't have to worry about that, right? So that all just happens under the hood, and your code on the right still looks really nice. And the other optimization is that in general, as we said, the coroutine frame will be allocated on the heap, but sometimes the compiler can optimize that away. And then if it kind of can see through the lifetime of the coroutine frame, and if it can prove if it stops existing by the end of the function, and the coroutine handle never escapes, then it can actually collapse everything and put it onto the stack. And so that is a really important optimization, because that gets rid potentially of a dynamic memory allocation and then deallocation. And so because of these optimizations that can happen, efficient coroutines have to be a language feature. So they cannot just be a library feature. But that's actually really nice, because the C++ code you wrote is nice and clean. The binary code you get is very lightweight, very efficient. You can use that on a bare metal machine because it doesn't rely on threads or the operating system or anything like that. It's like super low level. And it's nice and clean and fast. And these are pretty much all the bits you need. And that's what you get in C++ 20. There is only one kind of annoying thing about this in C++ 20 is that turns out that in C++ 20, the standard library doesn't actually provide a generator type and a promise type, because the committee didn't finish that bit in time. The good news is they are coming in C++ 23. So there is this paper, this proposal by Louis Baker and Corentin Jabot, which proposes a stud generator. And, this is a very, everyone looks forward to this proposal going in. So it's going to come in C++ 23. But until then, you kind of, unfortunately, have to implement this generator yourself. And part of the generator is a promise type, and so you have to implement that yourself too. Or, much better idea, just use a third-party library, like Louis Baker's CPP Coro library, which is what I would recommend. But when I was actually first had to deal with this coroutine stuff, I kind of got curious. I was like, yes, we should just use a library, but how does this work? So then I actually decided to actually try and implement these generator and promise type myself, just for this very, very simple case of generating a sequence, kind of in order to understand how it all works. And I have to admit, it was surprisingly painful. It took me all day. It worked in the end. I'm just going to quickly show you what that looks like. So this is what the promise type looks like, or at least, my implementation of it. And so this, so it's templated on the actual value, which, in the case we saw before will be int, but I just templated this to make it more generic. And you see that current value now is this box where the int will live, right? So that's actually where the int value is going to be stored in this current value member of the promise type. And so the coroutine is going to talk to this object in order to write that int in there. And so all of these other functions like initial suspend, final suspend, etc., that you have to implement are basically answers to those questions that the coroutine is going to ask you about how the reentrant behavior should exactly works when it yields, when it suspends, etc. And there's some choices you can make here. So, and that will basically, those choices will govern the behavior of the coroutine body. But this is kind of like very deep stuff for this basic example. I just went with like the default basically, which still have to type it out. But more interesting is this here, which is the yield value function which you have to implement, and that's the coroutine side of that communication channel. So the coroutine will call that function to actually, when you say yield x, so it's going to call that function to put the x into that box. And I'm taking that value here by const reference. You can probably also take it by move. You again have lots of choices here. But anyway, this works. And then we have the actual generator. And that's the object talking to the user code. And that's an implementation of the generator. So now you see here you have this coroutine handle, which is this compiler-generated magic type, which is this type erased pointer to the actual coroutine, which the compiler generates under the hood. And basically, essentially, the rest of this is a bunch of constructors and basically managing the lifetime of that coroutine handle, right? And then the only other interesting bit here really is this. So, of course, the promise type here that we just saw, and then this. And that's the user side of that communication channel. So that call operator, that's the operator that the user code is calling to get 0, 1, 2, 3. So that's the thing that actually returns the int, like takes it out of the box and returns it to your code, right? And again, you can maybe move it out of the function here. I'm returning it by value. You have all of these choices. So basically, don't try this at home. Like, I really cannot stress this enough. There's like a lot of subtlety here. There are a lot of choices to be made. And I just about managed to write this like very simple generator for this very simple case of just generating 0, 1, 2, 3. But I'm certainly not able to implement a generator for some more complicated use case. And so really just use a library where people who have thought this through have implemented this for us. But now we have this kind of generator, and when you do this, you get this user code, right? And that's really nice. That's really clean. That's really efficient. And that's how we can use them. And it actually becomes even more interesting when you have multiple coroutines, because let's say you're implementing a front end for some programming language, right? So you need to read characters from a file, then you need a lexer to turn them into tokens, and then you need a parser, which takes those tokens and builds an AST, right? So what you can do is you can either first read the whole file, then lex the whole thing, and then parse the whole thing. And then you have a bunch of classes which have interfaces and members to do all of these things. Or you do it with coroutines, which do it lazily and cooperatively. And so that's really nice, because then, whenever the parser needs a token, it calls the lexer coroutine, which just yields the next token, right? So it's just the lexer's in the middle of lexing, and it's just going to yield the next token, and then the parser can keep going. And then whenever the lexer needs another character, it's just going to call the reader, which is in the middle of reading the file, so it's just going to yield the next character to you. So it's really interesting because it's a completely different way of designing this, right? So you have this like cooperative, like different coroutines handing over different work to each other just like at the time when it's needed. And so that's really interesting. And it actually gets even more interesting when this happens on different threads, because now we have basically cooperative multitasking instead of preemptive multitasking, right? And that, like doing it that way, avoids another problem with multi-threaded code, which is commonly known as callback hell. And I work in audio technology, where we know this all too well, where we have like an audio processing thread, and we have to generate and consume like audio buffers, so we have all these callbacks going on. This is kind of the traditional way of designing this. And you use objects for this stuff, right? So typically you have an object which then registers a callback to another object, and then they call them back on a different thread, which is like a different thing there. And this kind of logic is kind of scattered across all these different places. You can't really debug that. It's really painful to work with this kind of code. And coroutines make this kind of stuff a lot simpler. So we have already seen coroutines that can yield and resume. Turns out they can actually do a third thing. And that third thing is exactly the thing we need here, and that's called await. And that's how basically you get coroutines to cooperate with each other in this very interesting way. Let's say we have a coroutine F1 and another coroutine F2. And now we have this third keyword here, which is co-await. By the way, as soon as you write any of these three keywords, co-yield, co-return, and co-await, that's how the compiler knows that your function's a coroutine. So there's no other syntactic marker for it. So the function's a coroutine basically is an implementation detail. It depends on whether you use any of these keywords inside the body. And that's really quite important. So from that, it follows that we can only co-await on a coroutine from another coroutine. So anyway, when you write co-await F2, what happens is that F1 suspends, just like it did before with yield, and it returns control to the call side of F1. But the trick is that now when F2 later yields, it's going to resume F1 from that point, from that co-await. And that's really interesting because F2 actually could be running from a different thread, right? So what you effectively get here is you get this thing where basically the way to think about this is that when you write co-await F2, what actually happens there is that you're registering a callback with F2, and then you return, you yield. And then the rest of the function body of F1 is essentially that callback, right? And so using this pattern is really nice because you don't actually have to write out those callbacks as like separate functions. So your code ends up much cleaner. So and the logic is together in one place. And this whole communication channel via callbacks is just completely abstracted away. And the only caveat here is that you see I wrote async generator here instead of generator. So if you have multiple threads going on, you kind of need a fundamentally different promise type because you need to synchronize access to this like shared value, the kind of box, to avoid race conditions. So you probably need to use locks and stuff like that, or maybe if it's an int, you can use an atomic. And that's really, really important. So the coroutines themselves, they don't do that for you. They don't care about threads. And actually, let me stress that again. Coroutines have nothing to do with threads, okay? So if your generator type is asynchronous and thread safe, but you have to actually do that or use a library that does that. And then you can call your coroutines from different threads, and then it will just work. And that's really cool. And I really can't wait for this to become a popular widespread technique, because it's not just for kind of audio stuff. It's also like, imagine networking code where typically you also have this like callback and you being called back on a different thread kind of thing, which I imagine a lot of you are writing code like that. And this is going to make it a lot simpler. All right, so we talked for quite a while about coroutines. We do have a few more features left to talk about. So the next really cool one is concepts. So let's talk about concepts. But before we can talk about concepts, we have to talk about functions. So here's a function. This is a function that takes an integer and determines whether that integer is a power of 2. That's a very useful function. In audio, for example, we need this all the time. And that's a really clever way of implementing that, which is using basically bit operations to determine whether exactly one bit is set. And because that's the way it works, it really should work for any integer type, right? But you don't want to just write this for an int. So how do you make this work for any integer type? I mean, you can write out all the 12 overloads, which is going to look like this. That's not great, but hey, we're writing C++, so we have templates, right? So we can template it on any type, and now we can use it with any integer type, right? So that's what we do, but now we have a problem, because what happens if someone decides to use that with a floating point number, like a double here? We're calling power of 2 with this 0.25 double value. And now you get this really weird error message saying invalid operands to binary expression. And then as the user, you just see template .NT, okay, why doesn't it work? And then basically what happens is that the compiler tries to instantiate that template with the double, and then it runs into an expression that basically doesn't work for a double, which is just like bitwise and there. And so then it basically gives you a compiler error inside the body at that point saying like that operand that doesn't work for a double. But then what the user needs to do, they need to actually go inside the implementation, find the error, figure out what's going wrong there, and that's really messy. The user shouldn't be looking at like somewhere inside the guts of the function body to figure out why it didn't compile, right? And this is actually a relatively easy error message, but if you have more complicated stuff, these error messages can get a lot longer. And if you ever use Boost, you know exactly what I'm talking about. How do we prevent this from happening? Well, we have a modern C++, so we can write a static assert saying this is only for integer types, right? So that's good. That's much better. Now we get a much better error message. So we kind of solved that problem. But let's say we actually want this to work for floating point as well, right? Because 0.25 actually also is a power of 2, right? It's 2 to the minus second. So we kind of want this to work. And there's actually a clever way of implementing this for floats and doubles as well, which looks like this. So basically, we can take the floating point number and decompose it into mantissa and exponent, which is what std frexp does. So if you've never heard about std frexp before, now you have. But that kind of sucks, because if you write it like that, you get this error message saying redefinition of function template is power of 2. Because even though you said, the one is for integrals, the other is a floating point, you did the function body with a static assert, but the signature of the functions is the same. So you basically redefined the same function 2 times, which doesn't work. And in C++ 17, really the only way to get out of this really unfortunate situation is using svine and enable if. And I'm sure, some of you have experience with this stuff. Let's see if we remember how to do this. Okay, so we need to enable if, one for integers and the other one for floats. So we have this enable if thing. Where do we put it, right? So we can put it into the return type like this. That kind of sucks because now we don't see the return type anymore, the actual return type. So we can put it into the parameter list, which is not great either, because now we kind of don't really see what the parameters this function takes, because it kind of obscures the parameter list. So my favorite method actually is to put this into the template argument list. I think that's the most readable variation of this, because it doesn't mess up the function signature. Unfortunately, this doesn't work, because it turns out that in C++, defaulted template arguments are not part of the function signature. So we get the same error again, that it's a redefinition of the same function with the same function signature. So what you actually have to do is, turns out that what I just said is not true for non-type template parameters. So you can make this a non-type template parameter. So you can make this an int like this, and that will compile. And that's what I've been using for quite a while. But then my friend Gaspar Azeman actually told me recently that that's not good, because ints can actually legitimately occur as non-type template parameters. So someone could actually put an actual value in there, and that would break this mechanism. So instead of using this, we should use a void star non-type template parameter. And that's the best way to do this. Okay, so this is ridiculous, right? It's impossible to use this. No one is going to remember all of this stuff. How do we even teach this or remember this? I certainly cannot do that. So the good news in C++ 20 is that we don't have to use this ever again, because you can just write a constraint like this. This is what we get from concepts, right? So you can just say requires integral, requires floating point. And these std integral floating point are now actually standard library concepts, which you just get in the standard library. So you can just use them like that. That's really nice. Of course, this is C++, so there's actually 3 different ways to write this. So this is the long form. There is also a shorter form where instead of saying template type name T requires, you actually just use the concept name instead of the keyword template. So you say template integral T. And then there's this really short form where you actually don't write the template head at all, but instead you just write it as if it were a non-template, just a function. But then you say concept name auto, and just in the parameter list. And you see that it's a template by this concept auto syntax, but it looks just mostly just like a normal function with a parameter list. And we also see why it makes sense to have these different syntaxes, actually. It's because they're for different use cases. So in the first case with the integer, we can write the short syntax. In the second case, we kind of have to name this type in the body because we are instantiating this mantissa thing there. So that's when we use like the longer form, which actually gives a name to this type, the t, right? So it makes sense to have these different syntaxes, but the point here is that concepts make sphere much, much easier. And that's going to fundamentally change the way you write templates. But that is still just scratching the surface. You can do so much more with concepts. So first of all, you can combine them. So, if you want to have an arithmetic concept, which actually is not in the standard library, but might be useful, you can just say, okay, a type that's arithmetic is just an integer type or a floating point type, right? So you can make a concept out of combining two other concepts. And then you can also combine them with and. Let's say you have, for some reason, you have a concept of any kind of number, but it has to be like not bigger than 8 bytes because, I don't know, because you're doing some low-level stuff where like you have to make sure that you're working with numbers that are fitting into, some kind of like small amount of memory or something. Doesn't matter. So here's your kind of small number concept where you're saying, well, it's any arithmetic concept. And also the size of that type has to be not bigger than 8 bytes. And actually, you see that you can not only combine concepts with or and, but you can also combine concepts with just any compile-time Boolean expression, like the size of, which isn't a concept. And you just can kind of combine them like that. And now we can write a function template that takes exactly the types that it can handle, right? This f here. And if you then, for example, violate this contract, then you get really nice error messages, right? So if you pass a double in, that's okay. If you pass a long double in, which has a size of bigger than 8 on most platforms, you get this really meaningful error message saying, error, no matching function can be ignored because long double doesn't satisfy that concept, because that constraint is not satisfied. So you get these like really, really nice error messages. And it gets even better than that. So you also have this thing called requires clauses where you can basically just directly write in code what the requirement is. So let's say we want to implement something like a hash map, and you want to template that on any type that is hashable. And if you want to define what hashable means, well, you say, well, hashable is any class for which you can instantiate std hash. And then if you call that std hash, it's going to return something that's convertible to a size t. It's going to return you some integer like hash value, right? And you kind of directly express that requirement to the interface of that class in code. And that's your concepts. And then any type that basically satisfies this interface will satisfy the concept and will work with your hash map. And that's really cool because previously you basically had two ways to express like what interface this T is supposed to be, supposed to have in order to work with the template. So either you could use, not use templates at all. You could use like a base class, like hashable, and you can inherit from that base class. This is what languages like Java are doing. Or if you use templates, then the only thing you could do is basically just kind of document those requirements in the docs, right? You could just say, well, if you want to use this template, then you need to implement this and that. But now you can actually write those requirements directly in C++ code instead. And that fundamentally changes how we design libraries. So earlier you had to think, okay, what classes do I need when I'm making a new library? Is it going to use templates? Is it going to use inheritance and virtual functions? Now the first question is, when you're designing a library, what concepts do we need to define, right? And then everything kind of falls out from that. And that lets you write much more flexible libraries and much more powerful libraries and much more expressive libraries. And once you start using concepts, you can't really go back anymore. And actually, some libraries are just outright impossible to implement without concepts. And the best example for that actually are ranges. So let's talk about ranges for a bit. Let's start with kind of the most basic level. Let's say we have struct users, and users have names and ages, basically. And then we want to sort those users by age, right? So we have sort, we pass in this begin and end iterator pair and a custom sort operator, which sorts them by age. as a lambda, and that's how we do things. But obviously, always passing in these begin and end iterator pairs to all these algorithms, that's quite repetitive. So what a lot of code bases do is they just introduce their own overloads for all these STL algorithms, which instead of begin and end, they just take one argument, which is templated, and that can be anything that has a begin and an end. And I know that the code base that I'm currently working on has this. Upsell has this as well. Like, I'm sure many of you work with code bases that have these like extra overloads just for convenience, basically. And just to get rid of this like begin and end kind of boilerplate. And the good news is that ranges give us that, right? So now we have those overloads in the standard library. We can just pass in the vector directly. But the cool thing is that that's not just an overload. It's actually constrained with concepts, right? So if you try to pass in something that's not actually sortable, that doesn't work with that particular algorithm, you actually now get really nice, really meaningful error messages. And then you have another feature here called projections, which makes this use case specifically much, much nicer even. So you can write it like that. So it turns out you don't actually need the lambda anymore at all, because these STL algorithms like sort, they now take a range. They take, in this case, a comparison operator, and then they also take a projection. So you don't need that lambda anymore. You just give it a projection. As a projection, you can just give it a pointer to member, to this age member, right? And that's just an int, and that's it. And then for the second argument, you can just use the std_less. Just that's going to work with an int. The compiler knows how to compare ints. And that's really cool. That's it. That's all you have to do here. You don't even have to write lambda anymore. And that's really cool. So let's look at the declaration of ranges sort. So you see in the last line, it takes these three parameters, like a range, a comparator, and a projection. And then you see it's a template, which is templated on those things. And it has a requires clause in there, which says, well, basically the range needs to be sortable. And that's, of course, a concept. So let's look at how the concept sortable is defined. Well, something is sortable if it's permutable and there's a strict weak ordering, right? Makes sense. Now, these are also concepts. So let's look at the permutable concept. In terms, something is permutable if it has a forward iterator, it's indirectly movable, storable, and it's indirectly swappable. And it's basically like this all the way down. And this whole library is just written with these concepts. And just imagine for a second what this would look like in C++ 17 if you had to like emulate this with std enable if. That would be ridiculous, right? Like, there are a handful of people in the world who have done stuff like this with like enable if and then macros around them and stuff like that. And I can only begin to imagine how painful that was. But nobody will have to do this ever again. With concepts, it's just code. You can read it, right? So that's really nice. Let's go back to our users here. Let's do something a little bit more complicated. So we have these users. Let's say we have a vector of users, and let's make this a const vector. So maybe, so we have a range that we actually cannot modify in place, and that's kind of to simulate a scenario where maybe that's actually not a vector. You know, maybe we are reading the users from the disk, or maybe we're reading them from the network, like one by one, right? So it's like a range that we cannot modify, something like that. And now what we want to do is we want to remove all the users that are under 18 years old and then print the age of all the remaining users. And let's try to write this with traditional STL algorithms, right? So we have this lambda, which is saying, okay, are you underage? So we filter them out using copy if, and then we transform that range to basically print the age of those remaining users. And that's like C++ 98 or C++ 17 also code. I mean, obviously, yeah, we have this lambda there. So it is more than C++, but it's pre-C++ 20 code. And it kind of seems that in order to write this a bit more compact, what we need here is kind of a transform if algorithm. But that doesn't exist in the STL. Because why? Because, you know, if you had to write transform if, you'd also have to write generate if and fill if and all of these other permutations. So you would have like an explosion of those. And this is just not the way to go. So how do we combine STL algorithms? And it turns out that without ranges, we kind of have to combine them eagerly in this kind of procedural style. So it means that you have to do the loop twice, right? Copy if is going to do a loop over the data, and transform is going to do another loop of the data. And also we need to actually copy the data like from the original vector into this like other vector, so that we can store the filtered uses, the intermediate result, and we have to hold that in memory. That's not ideal, and what ranges allows us to do is actually to combine that lazily, right, in a functional style. And that's going to look like that. So that's how you write it with ranges. So we have these ranges now in C++20, which are called views, and all they do really is they wrap other ranges, right? And they give you like a modified range, which is kind of wraps the other range. And you can easily combine those views with this pipe operator. And the important thing is here that they're lazy, right? So this code in the green box is actually not going to evaluate anything. It's actually not looking through the data. It's not touching the data. It's just a new range, which is like these like nested views. And the other thing that's really important here, like why can we do this? Because now instead of working with iterator pairs like begin and end, we're actually working with a single parameter, which is a range. And you can return one single parameter from a function. So that allows us to kind of thread this through this chain of function calls. And that's a very useful way to think about ranges. Like what they actually are kind of fundamentally is they're an interface to write STL algorithms in this functional style, where you can kind of combine things in this way that we had to write procedurally before. And you can copy this range like that, and if you want to actually print this now, so because the whole expression before that actually doesn't do anything. So if you want to actually print that, we can do it like that with a call to copy, and that will then actually loop through the data and evaluate everything, right? But the important thing is that it will loop through the data only once. And now if you're like chaining these views like that, you actually end up never writing any loops at all. So remember when Sean Perrin said 7 years ago, no row loops. Now in C++20, you really don't need to write loops anymore. But of course, because result itself is also a range, so it does have a begin and end. So if you really want to, you can use it with the loop, old style. It's going to work. You can put this whole thing, in a range-based for loop, for example, and because it has a begin and end, it will just work. And so filter and transform are just two examples. There are many, many, many more views in C++20. Here's another example. We have iota, which is another view, which is the ranges version of the iota algorithm. And if you know what the iota algorithm does, you can guess what this does. It prints 0, 1, 2, 3, 4, 5. And the cool thing about this C++20 version of iota is that you can print as many numbers as you want, and you don't need any extra memory for that, because you never have to store the whole sequence in memory, because it's just lazy. And that's another way to achieve what we did before with coroutines. And actually, in fact, it's pretty cool, because remember when we were talking about coroutines, there was saying that you're going to get a std generator in C++23 for coroutines. So that std generator is actually also going to be a range. So in this kind of in a really interesting and weird way, they are kind of two sides of the same coin here, right? Which I think is really, really cool. I don't have time to talk more about ranges and the different algorithms that there are, but I can highly recommend you this talk. There are other talks as well, but this is my favorite so far. Talk by Tristan Brindle giving an overview of standard ranges, which is 1 hour talk from last year's CPPCon, which is basically going to give you an overview of everything you need to know. So I highly recommend you check out this talk to dive a little bit deeper. We have one more big feature to talk about in C++20, which are modules. And of course, I saved the best for the end. But actually, before we can talk about modules, let's talk about headers. That's the stuff that we know. That's the world that we live in right now. So remember this generator thing that you wrote earlier for coroutines? Let's put this into a header, right? Because it feels like this is a template. It's like a generic thing. You might want to reuse it in different parts of the project. So we're going to put it in a header. And remember that like math, like power of 2 thing that we used earlier, that might be very useful in different parts of our project as well. So let's put that into a header as well, right? And now maybe we have a CPP file somewhere which is going to use both of those headers. And then we have another CPP file there, which is also going to use both of those headers, math.h and generator.h. So that's the typical scenario. And hash include, basically, what it does, as you probably know, is the preprocessor is going to just take that code and just copy paste it into that file, right? And that's going to be your translation unit. So it just really stupidly, takes the code from this other file and just copy pastes it into the file where you're including stuff. And so when you include the same headers in multiple translation units, the compiler is just going to repeat that process. It's going to put that code into all these different CPP files. And so when you then compile them, the compiler has to basically, in every one of them, parse and compile all this header code, right? So in coding stuff.cpp, it's going to parse and compile everything in math.h and generator.h, and other stuff.cpp, it's going to do the same thing over again and over again. And if you include those headers like in 20 different files, the compiler will have to parse and compile the same code over and over again 20 times. So on the one hand, that's really great because then all the translation units are independent from each other, and then that's very easy to parallelize. But on the other hand, that's really bad because that's really slow and you're wasting a lot of resources. And actually that grows non-linearly with the amount of files, so that's really bad. It doesn't scale. And now, if it's literally the same headers and they're included in the same order, then you can cache it. There's tools like Ccache. But it's just enough to flip the order of like two of them, like this. And now it's different code, right? So now, because it's just copy-pasting, it's going to copy-paste it in this order or in that order, and then those different translation units have different code, and the compiler again has to parse and compile it multiple times. And there's more fun, right? So there's more fun stuff. Headers can have cycles, right? So you can have these dependencies between headers because the preprocessor is not going to prevent you from doing that. It's just copy-pasting code. So you have to kind of write primer once or include guards, and sometimes you forget to do that or you mess up and you include things cyclically anyway, and then you get these weird errors, and then you spend 2 hours basically looking for the place where a certain header is getting included, and it's really messy. And then we have macros as well. So for example, if you define a macro above your includes, then that macro can leak inside the header. It can change anything in there. For example, if you define anybar, well, that can change the layout of some class inside generator.h, right? So then if you link those two CPP files together, you will have two different definitions of the same class. So that's an ODR violation. And that's like undefined behavior, except it's actually worse because it's undefined behavior on the linker level, essentially. In the standard, we call this IFNDR, ill-formed, no diagnostic required, which basically means you have no idea what program you get, but it's probably not going to be the program you wanted. It's probably going to crash or do something really weird. You're not going to see any compiler warnings or linker warnings or anything. So this is very, very fun to debug. And of course, macros can not only leak into headers, they can also leak out. Like, for example, you define a macro in generator.h, then that can leak out of that header, leak into the headers that you define below, or leak into the CPP file that includes it. And the other problem really with headers is that they don't support really any form of encapsulation, right? So that's the other thing. So if you're implementing this thing and like, let's say you have a helper struct here, which is just an implementation detail, but you have no way of hiding this in the header, right? If you're writing standard library code, you can prefix it with double underscores because then other users are not supposed to use that because that's UB. But most libraries are not the standard library, they're just other libraries. And so then people do this namespace detail stuff, which is essentially just a convention, which doesn't actually prevent anyone from going in there. And I also seen people use anonymous namespace and headers. So please never do that, ever. Because if you use anonymous namespaces and headers, then actually everything will end up in one gigantic big anonymous namespace. And then it just all explodes. So don't do that, please. And modules are really solving all of this, right? So now we can put our generator into a module. And the only things that are visible there are the things that you export. So you write export struct generator, and that's going to be visible to the user of the module. Struct helper, you didn't write export, so by default, it's just private, essentially. It's just hidden. And macros cannot get into the module. Macros cannot be exported out of the module. Cycles between modules are forbidden. So this module is completely self-contained as well, which means that you have to parse and compile it only once. When you do that, actually, the compiler will turn this module into this BMI file, which stands for Binary Module Interface, which is a bit confusing because you might think that a BMI is a binary file, like an object file, like .o or something like that. That's not the case. Binary here just means not text, so it's like an alternative representation of the code. which is kind of optimized for fast lookup of all the definitions in the module, so the compiler can compile stuff faster. So it's going to be some kind of data structure like a tree. It's specific to the compiler. It also contains the version of the compiler, all the flags that you set, even like which warnings that you set. So this BMI file is really not portable. You should not distribute this ever. It's just an implementation detail of your build system, essentially. Let me say that again. If you give this BMI file to other people, they will have a very bad time. So please don't do that. That's an intermediate step in compilation, essentially. But now you can actually use your module like that, right? So you can write import generator, import math. The order of imports doesn't matter anymore. And that's really nice. So like, I want to close this section by saying that modules are a massive feature. There's many more details. There's many more additional levels and ways to organize your code that I can't really cover here because we don't have time for that. But I really recommend you watch this talk by Bryce Elstern-Lelbach called Modules Are Coming, where he goes into all the gory details. Don't watch the CPP conversion, which is just 1 hour. Watch the core CPP version, which is actually 1.5 hours, where he covers more ground. And that really dives deep. So I recommend you check this out. But basically, the summary is that modules solve all these problems with headers, right? And they also completely change the compilation model and the way you organize the different components of your C++ project. So the only snag is that the C++ standard library itself is actually not modularized yet, but we're going to add that in C++ 23. And that's really the only feature that fundamentally changes the architecture of your program. That changes how we package our libraries, how we package everything like classes, functions. It's a huge ecosystem change. It actually is like a pathway to like moving on from header-only libraries as a convenient distribution mechanism. We can make package managers easier. So it's a huge ecosystem change, and I think it's going to improve things a lot. It's probably going to take time to be adopted, but I'm really looking forward to that happening. All right, I'm almost at the end of my talk. I hope I can get 1 more minute to just show like the last couple slides, which are...
Yes, 1 minute.
Okay, thank you. Long-awaited fixes. And I'm just going to mention one particular one, which is this one. Let's say you have a vector and you want to remove all the odd numbers, right? Very simple task. How do we do this? Well, I'm sure some of you know it's this thing, the erase remove thing. And that's probably the only thing in the standard library which I hate even more than std enable if, because everyone who's learning C++ stumbles upon this, right? So everyone writes vector arrays in a loop, erasing elements one by one. So you have to explain why this is slow. You have to explain this weird idiom and how this works. And then remove doesn't actually remove anything. It just moves things around. And then erase essentially like crops the range. And a lot of people think that remove is moving unwanted stuff to the end, which is actually not what's going on. It actually moves the element that you want to keep to the beginning, overwriting the unwanted ones. And I myself actually didn't know that until this year when I read like a blog post from Ben Dean about how remove if actually works. So this is horrible. And the good news is in C++ 20, we never have to write this again because we just have the std erase, which just takes a vector and does the job, right? So we can forget about erase remove and never speak about it again. And that's great. And I mentioned this as an example, but C++ 20 has a lot of stuff like this, where it just removes a lot of these obstacles. And that makes C++ easier to teach and easier to learn. And it makes everyday C++ code like this much easier to read. And that in itself will also significantly change the way we are going to be writing code. Thank you.